functional programming with Kotlin, some RxJava, the MVI architecture, a lot of different things that some people are doing. And what we're going to be covering is what does it really mean to write functional code. And this talk came from my interest in functional programming, so I don't have a specific background. It's not going to be about monads or category theory or all that. It's going to be more about some of the guiding principles behind functional programming and how they can help you in your code. And while this is labeled functional Android, a lot of these points can be applied other places as well. I just tend to use Android examples because that's where I'm working on day to day. I do have these slides up on my Twitter. My Twitter handle is @Gonda. They're also on SpeakerDeck if you're not on Twitter. So a little bit about who I am real quick. I'm an Android engineer at Buffer. We're a fully remote company, and our apps allow you to reach your customers and grow your brand on social media through your content, collaborating with your team, and measuring your performance. And then I am also an author for RayWonderLife.com along our Android and Kotlin team, helping making learning materials for them. So, why do people like functional programming? Three biggest things is, one, the features can be used to write cleaner, more concise code. We'll see how a lot of things can be made much more expressive. Also, some of the principles help with some of the problem parts of writing concurrent code, and it minimizes some surprises there. And then some of the principles also help things be more testable. So functional programming is not a tool or a library, but rather a way of thinking about and writing code. The principles say that it's declarative. You want to focus more on what the computer should be doing rather than how. And we see this all over in programming with abstraction, and we'll see some other ways of it here. You also want it to be explicit. You want it to be clear what is happening. Minimizing the surprises you get because maybe some Boolean was changed somewhere else where in your code that you didn't realize it, and now it changed behavior and you're surprised. Fewer the side effects, and the more explicit the code, the better. It also helps with concurrency and lends itself to it. We'll see how some of the concepts solve some of the things that make concurrency difficult. We'll also take a look at higher order functions. This makes functions personal citizens that you can pass into other functions, just like anything else, passing around logic. And then finally, functional programming leads into immutability. So once something is set, you can't change it. If you need something with a different property or something changed, you have to create a new one. And this helps to keep surprises to a minimum, especially when you're working on things. So to start off with, we're going to look at the idea of pure functions. So with pure functions, with a given input, you always get the same output. Even like an empty input is still an input. Every time that you enter something empty, you always get the same output. And everything that's required for the function is passed in. So passed in is a parameter generally. And this, in turn, can make things easier to test because you're only relying on the inputs of the function. I don't know if you've ever tried to write a test where, sure, you have your parameters that you're passing in, but so you have to set this field in this class and make sure this list is right in that other class, just to make the whole test work together, and it doesn't even feel worth it to write the test. This can help with that. So let's look at a fun example. Let's take a blender. And every time you add vanilla ice cream and milk and chocolate syrup, you want a chocolate milkshake, not a banana milkshake. And if you use strawberries, you want a strawberry milkshake. So here's our blend function. Let's find out if it's pure. We pass in some ingredients, and we get a milkshake ice cream are in a variable outside of the function. What if someone goes and swaps out vanilla ice cream for chocolate ice cream? And we're going to get a completely different milkshake. So it looks like this function is not pure. It's not solely dependent on the inputs to determine the outputs. So let's turn it into a pure function. Now everything is passed into the function that's required, so there's no reliance on outside variables. We can be more confident that this function will give us the result that we expect. There's no way some other part of the code is going to switch something out on us, giving us a different result than what we were thinking of. Pure functions also have no side effects. So similar to not depending on outside variables, it also doesn't change anything on the outside. This could include maybe changing a global variable, writing to a file or the database. A side effect could also be throwing an error. And because functions with no side effects don't change on anything on the outside, it can lessen the dependence on outside things, on the context. Having side effects in your code can make it harder to read and harder to understand. If there's information outside of the function that you need to understand in order to understand the function itself, you might be reading through the function, hopping to another part of the file to understand what this variable is and hopping back. If everything's contained in the function, relying just on the inputs to determine the outputs, it can be made easier to read. So let's picture our milkshake function. What if the function changed, say, the number of glasses on a shelf? Would that be avoiding side effects? So here's the function, but this time it's taking the glass from a collection of glasses. And that's kind of clearly a side effect. What if another part of the program was expecting that glass to be there to make a root beer float? And that could cause an unexpected error, and someone would have the root beer float, which would be very sad. So instead, let's pass in a glass. This way, we know that this function is safe and doesn't cause anything unexpected. It's a pure function with no side effects. And I realize that sometimes side effects can be unavoidable. Of course, there'll be a time where you need to write something from the database and retrieve it later. But pushing these functions to the edges of your code as much as possible and making as many of your functions pure as you can, will minimize these surprises and bring clarity to those parts of your code. So try to isolate them so other parts of your code don't have to rely on them. And then when you have pure functions that don't depend on context and don't change anything in the outside world, the order kind of stops mattering. Pure functions can be executed in any order, assuming that the output of one isn't the input of another. And when you don't have to worry about the order of things, that can also make things easier to read. You don't have to think about it as much as, well, why does this have to be called before this or that? And if they can be called in any order, this means they can also be called at the same time. So it makes spreading a bit easier. And again, you can't always have pure functions that don't depend on order in Android. You can't change the color and add a click listener to the button until there's a button there. But it's great when we can use these properties for our code. So, for example, making toast, mixing eggs, frying bacon, you think that you should be able to do these in any order. Doesn't matter. But to take a look at one of the functions, it's relying on a cook from a collection of cooks. And it turns out all three of these functions are doing this. So what if a cook is homesick and there's not enough hands? Or what if the wrong cook gets pulled in to make the wrong thing. You don't want the toast burner making the toast. And you think they'll always be there every time and in the right order, but other functions also have access to this collection. So we can change our functions to make them pure. Our cooks will be passed in as a parameter, which means they can be called in any order. If we have 3 cooks, they can all do their work at the same time, since we know none of the functions rely on the others. And then to bring up testing, we have the simplified testing from the pure functions, and then we also don't need to test for order because order doesn't matter. And if we forget about, well, what if we do it in this order? They're pure functions, so probably doesn't matter. Another important thing in functional programming is immutability. So this means that once something is set, it can't change. So if you have like a person with the name Victoria, you can't just go and change the name to Tori. If you need a person object with that name, you have to create a new instance of it. And this helps to minimize surprises. Things aren't going to change. If you already checked that the length of the name is greater than 5, later on in your code, you know it's still going to be greater than 5. It's not going to be less than 5 because someone else changed it to Tori instead of Victoria. So we're visiting our diner and our food examples. How strange would it be if somewhere between the griddle and the table, a veggie burger turned into a beef burger? That wouldn't be right and rather unexpected. So let's see how we can avoid that. So here's our burger. We have our type of burger as a string, and notice that we're using a var, which means that this type is mutable, so it can be changed. So after we make the burger, we can change what type it is. So imagine what unexpected things can happen from that, like getting the wrong burger delivered to your table. So let's make this immutable. In Kotlin, all we have to do is make this a val. That's immutable, you can't change it. And then strings are also immutable, so we don't have to worry about the string object itself changing. So now, if we try to modify the type, we won't be able to. If we want a beef burger, we have to create a whole new burger. Makes sense. And then the fun thing with Kotlin is smart casting. It pays attention to if something is mutable and could have changed. So let's take a look at if we have our mutable burger and then the type is also null. We have our burger and then we check if it's null, but we still can't call something on it because Kotlin knows that technically sometime between our if statement, our check, and calling something on it, length in this case, that it might not be non-null anymore. Something on another thread could have changed it. And it could happen. It might be unlikely, but it could happen. And if we make it immutable again, and it's still null, once we check for null, it knows that it's not going to change. It's like, even if something else has access to it, I know it is immutable, so it's going to stick the same thing. And this is great. You can see what wonders this can do for preventing unexpected behavior, especially when it comes to concurrency. But there's still another thing we have to watch out for. We made it so that we can't reassign the property, but what if the object that's assigned to it itself is mutable? So imagine we have an additional property on our burger, which is toppings. Now, we can't assign a new list to it, but if the list is mutable, like default lists in Java, we can change the items in the list. Again, this can lead to unexpected behavior. So in this example, we can change the items in the list even though we can't reassign the list. So it looks like this customer is getting onions whether they wanted them or not. And they don't want to just remove the onions because they can still take the onions even if you take the onions off the burger. So we want our burgers to be predictable. So how do we do this? In Kotlin, it's pretty easy. Kotlin has both mutable and immutable list types, with the default being immutable, which is great. This means that after creation, we can't change the contents. So easy enough. If we had mutable objects within the list, we have to follow down the nesting, making sure things are immutable. But because we have a string here, we don't have to worry about that. So now this customer isn't getting any extra onions, but maybe someone else who did order onions is. So how do we handle this in real life? So here's an example of when you might want to change a value. We want to change the type of a burger, but without creating unexpected states. You can do that by creating a copy of the burger, changing only the type. And with Kotlin data classes, they automatically provide a copy method. You can just pass in what properties you want different in the copy. So it makes things pretty simple. When talking about copying things and all this, the biggest question I get is, well, what about performance? And in a lot of cases, it's going to be small things like this, so you're not really going to notice a difference with performance. Maybe if you had a long list that you're copying a lot, or just copying the same object over and over again, and maybe it's a really big object, then maybe you could consider it. But in the majority of cases, especially if you've architected your app well, it's going to be smaller things that aren't going to affect your performance. Okay, concurrency. It's hard. But a lot of things that we've talked about can help with it. Using pure functions, not changing the state of the world outside or depending on it, keeping things immutable, all these help avoid unexpected states that concurrency can paint you into. So keeping up with our burger example, making one burger shouldn't change the toppings of the second burger. When one person orders a veggie burger with tomato and someone else a burger with lettuce, they should get what they asked for, not a burger with tomato and lettuce. So let's imagine we have both of these orders. We get the toppings together for one and then for the other, but somehow they end up on the same burger. And that wouldn't be right. That'd be unexpected. So how can this go wrong? We have a function that adds toppings to our burger and then emits or sends it out. Notice we're using our mutable version of our burger, so the type can change and the toppings can change, and it has the side effects of changing the burger. Now, we have a busy kitchen, and we want to take advantage of working on things concurrently. So we can prep both burgers at once. We're going to use RxJava for this, just because it can simplify threading. I will explain what you need to know for this if you're not familiar with RxJava. So we have first that our function is adding the toppings to our burgers on their own schedulers. Think of these as maybe two different cooks in the kitchen. In your program, this might be a worker scheduler or an IO scheduler. And then we're using merge to create a string that emits the results of both the add toppings functions. This can be thought of maybe one person on the wait staff delivering both of these burgers. We can't guarantee what order the burgers will be ready, but whenever each of them is ready, they'll be delivered. And this might be done on a separate delivery scheduler, say your UI or your main thread. So I don't know if you spotted the issue, but both cooks are modifying the same burger. So someone's going to get the wrong order. So let's see how this can be solved with immutability. Using our immutable burger, here's the modified add toppings method. Now, in order to add the toppings, we need to create a new burger because we don't always want to be modifying the same one. With this change, there will be 2 different burgers delivered, each with the correct toppings. By making our burger immutable and using a pure function, we're able to work concurrently without that unexpected behavior. And then you can apply these principles to coroutines as well. I won't get into an example just for the sake of time and redundancy, but you can apply these principles other places. Next, we have higher order functions, which I feel like is one of the funnest parts of this. With higher order functions, you can pass a function in to another function. So passing around logic as you would data. There's a number of places where this could be helpful. In Android, the classic example is setting an on-click listener. These higher order functions can also be really helpful if you have some code where maybe the beginning part's always the same and the end part's always the same, but the middle logic can change. We'll take a look at each of these examples, one for each case. To start with, we'll look at the case where the beginning and the end might be the same, but the middle parts are different. A simple example on Android might be writing to shared preferences. So let's take a look at a series of events to cook potatoes. We're always going to wash and peel the potatoes, and they'll always be eaten. But how they're cooked can vary. We have a function that makes these potatoes, and then takes another parameter as a function that describes how we want to make them. And then to declare that we want to pass in a function with a parameter, with the parameter name, an arrow, or the parameter type, an arrow, the return value. And then inside we call it like any other function, we call it potatoes. So here we have a make potatoes function that takes potatoes and a function in, preps the potatoes, and then cooks them according to the function that's passed in. And then we eat them because who doesn't want to eat potatoes? If you don't want to eat potatoes, I will eat all the potatoes. And then to call the function, passing in the potatoes is normal. To pass in the function, or the lambda, you can take the logic, the curly braces, you can name your input variable. Here's potatoes, we have an arrow, and then we're going to fry the potatoes to say, make hash browns. And this is kind of a verbose way of calling it. There's other more concise ways, but wanted to explain the different parts of each part of the call. So just like that, we have a function to make and eat any kind of potato without the repetition of including the prep and the eat word for each different kind of way to cook it. So just look at the power that they give us now. And then for the other common case is for using a higher order function, is for setting a listener. So you can replace a single function interface, often containing logic to respond to an event, such as like a click or something being emitted from an RxJava stream. So here's our situation here, is we have a listener for when a customer has finished eating. So we can clear the dishes and bring the check. We could pass in an abstract object with a single method that contains all of this, but we can take the cleaner approach of passing in this lambda. So here we're setting our unfinished eating listener, and with it we're able to wait until the customer is done eating before performing these actions, because it would be kind of weird to do so. And those are all of the properties that we're going to cover now.